main.native, put the output in target.bsv. So this is now the BlueSpec code, which looks a lot like what we wrote with different syntax. And let me upload this to a server that has the electronic design automation tools that we'll need. So I'll copy target.bsv into this server, and nope.
Do you expect students to do their homework?
I do not expect anyone else to be able to run these programs. It's just too much work. You can get a free academic license, but for a 100-way license might have been asking a little much. Okay, so let's SSH this server. So I go in here and run a setup script.
Are there non-proprietary backends for this stuff?
Almost. We're working on it. So, okay, what do I have here? Should have this now in target.bsv. Same code we looked at before, magically transported across the internet. And so let's try to build this. And I think we saw this before. The output mentions two modules we don't actually need. Let's get rid of those. And it mentions something called multiply unsigned. I'm not sure why that is, but I found I can just replace this with a star. Okay, so now that builds. And then I need to put in a little harness at the bottom, which I've generated in advance, just this code here. Let's drop it in. So I'm defining a module that implements the final output method that we assumed in Calc, sendac, which takes in 32-bit number, and it calls display to output that on the screen. So I'll recall again, we saw this display last time. It's really a function you use for debugging. If we tried to actually synthesize this to hardware, we'd get yelled at for calling display. And so then our final module, make tester, implements the empty interface, and it instantiates the printer as well as our top-level module from Calc, telling it, remember that method you said you needed to send your output to? Well, use the one in this printer that I just made for you. All right, so now this should work a lot better. It takes a while for this to run. It is generating C++ code customized to simulating this particular module. We got a little chatter about the scheduler having some tough choices to make. Thank you, scheduler. And in 10 seconds or so, we will have our executable simulator, and it'll print out an exciting sequence of numbers, which I think is the correct one. This is probably a good delay slot to ask if there are any questions up to this point. Too bad. I don't know how to do that. It might be somewhere easily accessible, but the stages I'm running here, honestly, have mostly been outsourced to my students until this week, so I'm not sure entirely what's happening right now. Zach, did you have a question?
Oh, I was just going to ask, how hard is it if I built an entire processor to then tape out from this?
I think it's about as hard as it should be.
I guess maybe for a point, people are doing this, right, with RISC-V and BlueSpec and generating.
Yeah, we have a taped out BlueSpec implementation of RISC-V at MIT. It was mostly some of our friends in EE doing the physical work, and I don't know what they did or how hard it was for them. But it wasn't impractically time-consuming. All right, simulator ready. Wow, look at all those numbers. Did anyone see a bug? I think the first two we could sort of manually check. We added one and then doubled that, and added one and doubled that. Yeah, it seems to be working. Proof by induction. And it's pretty easy to get this to run on FPGAs, or at least it's pretty easy for me to say to my student, make it run on FPGAs. And that works too. All right. So I want to switch next to an example in processors that will also be a three-stage pipeline, but we'll be doing processor kind of things instead of add and multiply numbers, boring things. And I'll switch to the Blackboard to map out the basic plan for that theorem. Any questions that we should do first while I have Emacs open here? All right. I will now press all the buttons over here to make the screen go up. Okay, so pretty much every real processor that you'd find in your laptop, for instance, does use pipelines for performance reasons. And we're just going to use a baby version of a pipeline here. It has 3 stages. You typically have many more in a commercial chip. Let me explain what stages we'll use. The first stage is called decode. Let's think of this like a module, just like the ones we were looking at. It contains the program counter as a register inside of it. And I'll write IMEM for instruction memory. Decode will, over and over again, read from the instruction memory at the address denoted by the program counter register, and then increment that register eventually. So then, what's next? There's a FIFO that this thing is dropping information into, and it's dropping formatted records that contain, for instance, which operation is being run, what is the first source register, what is the second source register, what is the destination register, and so on. So basically this one reads from memory and then decodes the instruction format into a bunch of fields that are what we actually want to know to run the instruction. Typically processors will go even further and have 2 separate stages, one that reads from memory and another that decodes what came out of memory. But we're keeping it simpler here. And so for instruction sets like x86, it's really quite a lot of work to decode. For instruction sets like RISC-V, much less work. We are going to abstract out the actual decoding function and just assume there's some commie code that breaks a sufficiently large string of bits into these different fields. And then we are going to feed those into a stage called execute. You can probably guess mostly what this one does, and this is the stage that talks to the data memory, which I'm writing as DMEM here. It'll do both read and write operations as appropriate for the instructions that we're running. I'll draw a little module here called RF for register file. Execute needs to touch the register file, but only in read mode. The execute stage only performs register reads. It doesn't yet do the register writes because it's going to enqueue the appropriate writes into another FIFO that stores a destination register and a value that goes into it. And then these are dequeued and executed by a module called writeback, which also needs to be able to access the register file, this time in the right direction. Okay, so think of all 3 of these stages as constantly executing in parallel, communicating through these queues. Any questions about this design of a processor? Yes?
Can't write to the instruction memory and you can't change the program counter, is that right?
The program counter is being incremented every time we decode. And in this simple system, I'm not actually going to have any conditional jump instructions, for instance, so it's straightforward for decode to keep bumping up the program counter. And yeah, we have separate instruction data memory. Instruction memory is read-only here. Yes?
Does this architecture even support unconditional jump?
It doesn't support jumps at all, that's true. Yeah, we're just going to run straight line code. And you get into fancier things like branch predictors when you want to make this work with jumps, which are even more interesting for conditional than unconditional jumps, and cause all sorts of fun security problems, which we are avoiding by construction here. Yes?
So is the lack of jumps in this one just for demonstration?
Yeah. Yeah, we have a verified implementation for the whole user-level instruction set of RISC-V, which does all the real things it needs to do, but a little hard to present in the time available here. Okay, let me also, before we go into the proof, give some of a sense for why it's useful to divide up our implementation like this. Why not just have one big function? Why not take the equivalent of the spec that we proved for the 3-stage pipeline before and make that the real processor. So let's just think about how the execution of instructions proceeds in time. If we had one big block of code that runs for every instruction, then execution would look sort of like this. We would be sequentially running the decode part, the execute part, the write back part, then do it again for the next one. And so it would the time needed to run an instruction would be based on the full length of the data flow path through all three stages of this pipeline. Whereas if we do it in the nice pipelined way, then what we get instead is effectively, modulo the additional overhead that the queues introduce, we get to overlap the execution of instructions, and therefore, at some level, so think in this version, how frequently is an instruction finished? So if we imagine each of these takes one time unit, which is a little bit of a simplification, then it takes every 3 time units an instruction is done, whereas in this version, every 1 time unit an instruction is done. And each of these individual stages takes much less time, takes, let's say, 1/3 of the time of the original one over here. So this is a win. We really improve the throughput of instruction execution. But there is a catch. Well, the way I've drawn that pipeline so far is not quite correct. Does anyone see anything that could go wrong? If we imagine all the stages are really running in parallel.
The writes and reads to the register file need to be synchronized.
Yeah, this is effectively the classic kind of concurrency bug that you'd expect sophomores to make in a programming class where they haven't seen locks yet and they're really optimistic and try to touch everything at once, and sometimes they get the wrong answer. So how should we fix this? Let me first just demonstrate one case with the wrong answer to make this concrete. Imagine that the program is, let's say, I'll just pretend we have registers A, B, and C, and D also. The program reads B into A, then adds A and B and stores that in C, and then also copies A into D. So with this sequence of instructions, at some point, the pipeline state would be like this one. The first stage is trying to decode D gets A. The second stage is trying to execute C gets A plus B. And the third stage is trying to write back A gets B. And we have this shared register file. And the middle stage is trying to get the register file to tell it what is the value of A. And the last stage is trying to tell the register file what the new value of A is. So we sort of have a race condition here in software terminology where we have 2 concurrent accesses, at least one of which is a write, and that tends to lead to trouble. And the way this would actually run in the BlueSpec kind of semantics is that this code is fine. The read here would return the old value, and the setting of a new value would only take effect after this clock cycle, after this instant in atomic execution time. So we really would get the wrong answer here. So let's reconsider this design. What should I add in here so that we're able to avoid this problem?
Okay. Add something between. I mean, like have something like proxy level to a register file, like. More specifically, I'm thinking about like something like a reservation table.
Okay, you're suggesting a new part of this diagram called a reservation table, and it's called a scoreboard in our development. I don't know if those are distinct concepts. Let me draw in something called a scoreboard, and we'll figure out what it does. Scoreboard. scoreboard. What the scoreboard is it's just it has 1 bit per register that's going to record, has someone told us we're working on that register at the moment. And then the execute stage needs to check that the sources are not claimed at the moment. And it needs to claim the destination. And then the write back stage needs to unclaim the destination. And now I think this is a correct diagram. It means, by the way, we won't always realize the perfect interleaved execution up there. Sometimes some stages we'll have to sit around waiting for other stages to finish, but at least we should get correct answers now. And reasonable, well-written code, we hope, has enough instruction level. It avoids close data flow dependencies often enough that we do get this nice pipeline interleaving most of the time. All right. Any questions about the final design we've arrived at here? Yeah.
When we give the spec, will we give the sequential version?
The spec is just going to be atomic execution of the whole instruction. Yeah. And I'll work up towards the spec appearing on that side of the board. But it's just like the spec of the simple pipeline example from before with different things happening in the stages. So I'll also follow the same proof structure from before, and I'll just kind of diagram it here. Let's imagine I want to build one big pipeline stage called DE for decode and execute, which is then connected to the write back stage. And there's a register file that now both of them need to be able to touch. And still there's instruction memory and data memory. And there's the scoreboard, which both of these need to be able to touch. So we can combine those stages, and then after that, I will finally get to the, I'll just write it this way, do decode, execute, write back, which has everything attached to it. And has a register file too. So these are the 3 main stages of the proof. We'll use transitivity of refinement to show we can shrink this to this, shrink this to this, and this one is going to be so short and simple that we aren't too worried that we get it wrong. And then the key thing to do is, remember the proof we did about the simpler pipeline system. For each of these steps, we want to identify crucial invariants that hold on the left, as well as a mapping from, at every step of execution, state on the left to what the corresponding state will be on the right. We'll do that twice for each of these steps. Yeah?
Given that here the execute and write back stages are much tighter coupled than the decode stage, the execute stage, is there a particular reason why you parenthesize them the opposite way in your middle design?
Let's see. Good question. I think it's probably easier to merge the first 2 stages because the first stage doesn't touch the scoreboard. So the scoreboard behavior remains the same. That might be it, but it might also just be an accident that we picked this order to do it in. Yeah?
What do you need a scoreboard for the memory as well? Improves this correspondence?
Let's see. No, because execute and write back stages both touch the registers, whereas I didn't mention this. In this design, only execute touches the memory. So there's no concurrency issue. If there's a state element that only one stage touches, then there's no concurrency issue with it. And we say that the data memory is owned by the executor here, and we avoid that issue. All right, let's see. So what makes it okay to merge these stages